things in a little different way. I put a kind of a interesting topic in there, wood welding. We're going to get into that and talk about how that's done, how we make short beams into long ones. And we're going to talk about how connectors should be designed, and things like what's the right amount of torque on a nut and bolt, and what's the right amount of torque on a lag screw, and what's the right size pilot hole, and on and on. That's going to set up the fundamentals, a little bit of the fundamentals of designing with wood, particularly in regards to connectors. And then we're going to go full steam into a bit more detail on fixed end moment connections and how we weld pieces of wood together and do it effectively so that the strength of the connection is 125% at minimum of the parent beam. And so that's where we're headed today. And I'm not in a race to get through all the slides, because this session drifts to the next session next week. And we're just going to work our way through it. As you develop questions, as Dave said, just put them in your chat bar, and I'll see the chat numbers go up and up in terms of the questions. And I might stop part way through and take a bunch of them because I want this to be a productive session as we learn more about wood. You know, at the end of the day, designing a girder for a bridge or a main carry beam for a building, the design of that beam is really not that complex. The fact of the matter is, you know, you get your demand, you calculate your resistance for MV and EI required, for example, on a vertical load on a horizontal beam, and you size the beam. And that exercise is probably the easiest of all the exercise. 90% of the effort in designing bridges and buildings goes into the connections, and the devil's in the details. We're in the process of writing a textbook for NRCan right now in conjunction with several provinces in Canada on how to put together the proper detailing for timber bridges. Detailing needs to consider not only the strength passage from one element to another, but the longevity of the structure too. If your connectors are not providing for longevity and for durability and for fatigue resistance, they're a disservice to the bridge. Yes, I designed the right size element, a 12 by 24 solid sawn, took a 9-meter span. I had 13 of them across the width, and I had a transverse plank, spike plank deck. And at the end of the day, it got the traffic across the road, across the gap. But if that traffic crossed the gap for 20 years and all of a sudden the deck was gone, the girders were cracking because of vertical fasteners that caused a reduction in MOE and compression and excessive deflection, more stress and tension. If that's what the design created, then timber will be seen as a false work, as a temporary structure. It won't compete on the durability side of the equation. And so connections and the way we assemble the bits and pieces in a timber bridge become critical for us if we want longevity. And an attitude can't be, well, I've designed this a certain way and it'll last me out. That can't be the attitude. If the average age of a timber bridge in Canada is 82 years, they've lasted us out already. I've been in the business 45 years, and I hope to go another 3 or 4 or 5 years yet. And so let's say I spent 50 years in the business. We want a timber bridge to go 100 years, longer. These covered bridges in New Brunswick are over 100 years, many of them. So we want longevity in our timber bridges. We want them to compete effectively against concrete and steel and become an equal player in the material supply side of bridges. We often say, well, okay, timber just doesn't handle the impact loads, or it doesn't handle the durability question, and it decays. And if I lay it on the ground, it decays. And it's really not a permanent material. But the fact of the matter is, in the design of our connections, in the design of our structure, we can ensure that a timber bridge lasts 100 years. If they're lasting 82 years on average right now, with many antiquated and old technology methods used to join pieces together, imagine how long they can last when you do it right. And so with that, I'm heading into the session. This is a gap right here at Dillman's Bridge, it's called, down near Meagher's Grant in Nova Scotia. It's a gap where, let's see here, I'll just slip outside this for a minute and go over here. to this guy right here. And if you're able to see my screen, you'll see this is Wise Road as it comes up to Meagher's Grant. And here's this old single lane steel through truss bridge that went across the Musquodoboit River. And, you know, it had cast in place concrete foundations in the 20s in terms of span, meters. And it
Hey,
did
Dan,
fall. Yes, not showing.
I don't.
Hold
It's
on.
not showing.
Hold on. Hold on. New share. I know better. Share. There we go. Better?
Yep. See it there.
Okay.
Now.
Sorry, guys. I just didn't reshare. So this is the Wise Road. It's coming up to Meagher's Grant, and this is a single lane steel through truss bridge that come out of the repair and basically had to be replaced. And that's what we're talking about with the replacement of this one bridge called Dillman's Bridge that I want to feature a little bit today in some of my connector discussions. And I'm going to show you a bit more about that here. I'm going to stop the share and go back to sharing on this. Okay, this is a little bit of a disadvantage, isn't it? So here we go. You see right here. And this is the bridge 35-meter clear span that's a pre-assembled. And I just talked just a minute about this because this is a big part of the equation, this pre-assembly. Why is it a big part of the equation? Well, we want to make sure that all of the joints and nuts and bolts that have been put in the bridge are working effectively together, and that you've got them sized right and that you've got them assembled right, so that when you take it apart and treat it with an oil-based treatment, not a water-based treatment, we want an oil-based treatment. Why do we want oil-based? We don't want the wood to swell. If we treat it with a water-based treatment and we have pre-machined the wood, then the wood will pick up moisture, and because it's hygroscopic, it will swell, and the placement of all of the pre-machined holes and for the nuts and bolts will change, and the bridge won't go together well, and we'll have to bright a bunch of holes. What's that mean? Re-drill them on site. And when we re-drill them, we open up bright wood, and that bright wood will decay as if it was never treated, because it's not treated, and the bridge connector system will contribute to the reduction in the bridge's longevity. We don't want that. So part of not having that is to pre-machine, pre-assemble the whole bridge. This is 35-meter clear span. Then take it apart, letter and number it, send it out for an oil-based treatment to required uptakes. Use a wood, say like Doug fir, coastal Doug fir, that has not got aspirated pits, so you get deeper travel, the oil-based treatment, laterally or depth-wise into the bridge. Incise the beams so that they have more end grain exposed and get better uptakes, like 9.6 kilograms a cubic meter, and good depth, like let's say 1 inch to 1.5 inches, with a 5/8 inch deep incising placement at certain ratios. And you get this bridge treated with the right uptake. It's post-treated, pre-machined, pre-assembled, so that it provides for longevity. Now, this bridge then has to be taken apart, it's treated, it's shipped to site, and of course, it's going to go on this gap. And you can see here, we have to create a vertical profile out of our beams with the required camber, because the wood is going to accept dead loads, its own self-weight, and it's going to deflect. So we develop a camber in the beams, which you can do easily with wood. And in that created camber, we provide for dead load deflections, so that we can use an L/400 live load deflection with the residual camber post installation. And you can see the number of girders going across here. Again, the girder design becomes relatively simple. Not as simple in this case because they're high strength fiber reinforced, so they're a little different. They span longer distances, carry greater loads. And you've got a transverse deck, a TL4 truck crash proof rail system, crowning on the asphalt, and you've got this cross section showing you what's going to happen. Across the width here, you've got 10 plumb piles, that's verticals, 2 wings apiece on each side, and then you've got this cap on top of the piles, and the girders are placed here strategically so that you get some good balance in the vertical load. This shows you a side view of the bridge where you've got these FEMs, fixed and moment connectors. Now, these are exposed. In this bridge, we have industrial grade beams, not architectural, because Architectural isn't critical. It's about getting the job done more than pretty. And these FEMs are exterior FEMs and internal. Well, you can design both. But today, for simplicity in this course, we're going to look at external FEMs with some internal fastening. And these FEMs are placed at different strategic positions. So because you can ship easily a 17-meter beam, we're going to make these sections with the longest being 17 and 2 different lengths. Why are we doing that? Because we want to stagger the FEMs so that any one point across the width of the bridge, we don't have the FEMs all lined up. That's just a safety and redundancy thing. It doesn't mean we can't design them. We don't know what we're doing. None of that. It's about safety and redundancy. So we have them staggered. And so one will get a little bit more moment than the other. The other gets a little more shear than the other. And so we take the maximum shear requirements and we take the maximum moment requirements and we design the FEMs to handle those as well as any lateral. Now it's assumed the soffit here is above our SL 100. So we're not going to have a debris field. So I'm not going to bring into play lateral loads on the bridge in this discussion today in this 2-hour set. But you can see lots of lateral bracing here, transverse deck, and we've got these girders underneath. And so after we get the piles driven, here we are driving them. This is a diesel hammer. We're driving the first drive of the piles to diesel is about 14 to 15,000 foot-pounds. We're driving with a diesel. We know we have till down here 8 to 10 and around 10, maybe 12 on the other side. So we're driving different length piles, 56 on this side, 40 feet on the other side, because we want to get into the till. And we've designed a sturdy boot. We kind of got a little issue on this bridge because these are COVID piles, I call them, because during COVID days, finding tip bearing piles was a little bit more difficult. And we ended up with utility pole piles, and they're big and robust. And we had to redesign the boot. And this boot was put on purpose so that we can get through the top layers down into the till and embed these piles into the till a good 1.5 to 2 meters, because we want good tip bearing. They're tip bearing type piles. Some people might ask, well, what does that mean, Dan? Well, in piles, you have 6 different formulas you can use to calculate a pile capacity. They use either tip bearing or side friction. And with timber, because it's got taper, different than a concrete or steel H-section pile, you have displacement as well. So you get these 3 factors that tend to provide for a resistance for you, and you drive piles against that resistance. And typically in the marketplace, we consider a typical timber pile to be 25 ton rated. We usually try to drive them with dynamic energy to 3 times that. We look for the pile to be stopping up on finalization drive with 1/8 of an inch and 3 repeated blows, 6 and 1 inch. These were driven first with a diesel and then finalized with a drop hammer. We took the heavy hammer over 3,000 pounds, raised it to 6 feet and dropped that and made that our finalization. The target was 20,000 foot-pounds, and we were using 4-foot drop with a heavy for that. So we just over drove in a way, even though it kind of ruined the tips up there a little bit, but that didn't hurt us because we had pile to play with and we drove them in the ground. This shows you us doing the PDA testing. I assume you're seeing that, Dave. Are you hearing and seeing that, Dave?
Yeah, you can. I can see it. I can't hear it, but the visual is good.
Hold on. We're going to play that again because I have to go over here and share sound. Okay. Can you hear it now?
Yeah, everything's good.
Good. So you can see them here. This is a drop hammer finalization. You got a donut up top, and you got the side markers showing how deep it is. You've got your PDA set up, your dynamic pile analyzer, and you got a pair of transducer strain gauges and a pair of accelerometers, and you get the right specific gravity, the right time of flight for your wave, and you can calculate kind of what's going on. The PDA is a little hard with timber because timber creates this displacement field. It doesn't tend to relax the same way a concrete and steel pile does. So there's differences about timber that make it a little harder to use a PDA with, but bottom line, we drove our piles. And so we ended up with these piles all driven here, and this is the way it sits here in the last few days. They got to be trimmed down after we survey in the right height and placement, because the placement of the girders, you can see we have 8 girders and 10 piles. We want these outside girders to kind of share a little bit better between these outside piles. The heaviest load on a pile on factor, 245 kilonewtons or 24.5 tons. The lightest around 111, say 115 or 11 tons, because there's different loads on the piles from the girders. There are different maximums. And so we've got these piles in place, and here comes the making of the beam. And so we're going to make this beam, and this is the raw steel. These are the routs and the shear plates for the different connections. And we make this whole beam in the shop. And then after it's made and assembled, we send the wood out, we take it apart, send the wood for treatment, and the steel for galvanizing. Well, why do we do that? We want everything to match. You don't want to have different things trying to match up, because that breeds for sloppiness in the connection. Now, in this particular case with Dillman's, we had a really interesting and exciting thing happen that was important. That is that there was a couple extra big girders that we used to create a lift beam assembly for the Milky's bridge I showed you in the previous edition, which was 1920. You know, we talk about timber bridges not lasting. What's that about? This timber bridge was built over 100 years ago. Well, who says that timber doesn't last? There's lots of concrete bridges blowing up at 40 years. What's that statement doesn't last? And what's the statement that it can't carry loads? We raised it from a 5-ton to 30. It's not about those things. Those are design things. If you know what you're doing when you're designing timber, you can design it to go long spans, carry heavy loads, and last 100 years. It's about design. But if the engineers are taught in steel and concrete and not timber, they get out and do what they know. It's not their fault. They're good people. It's not that people are, not good people. They've just never been trained in timber. And so because of that, they stick with what they know. And I'm about changing that. So you can see here a few interesting things. This is 2 of these beams, kind of like the Dillman beams, with the FEMs here. They're on rollers because we rolled them out into the bridge on tracks because they were lightweight enough to go onto the bridge with its existing capacity when it was disabled. And then we put rods down through the deck and basically used the beams to lift up the bridge. And we used stiffness to measure how much load we were picking up. And we picked up 100 tons with 2 of these girders. And they had FEMs at different positions, as you can see here. They're staggered for redundancy. And so what we saw when we lifted up the bridge was something interesting. In the Canadian code, there's no slip modulus or slip deformation or distortion calculations for shear plates or bolts. It's only in NDS in America. And because we went to L over 120, way beyond L over 400 in live, we had a chance to see something going on we didn't like, or I didn't like. And that is this little bit of separation here in the butt-to-butt joint. And so I had this joint design as a mechanical joint, not a wood weld joint. And I decided for Dillman's that I was going to change this and go to a chemical joint or a wood weld. Why? Because I didn't want to see this opening going on. Well, was the opening significant enough? Not likely, but I don't like the durability side of it. I don't like the soffit height side of it that could take place with an additional inch or 2 of deflection created by this. So I moved it to a wood weld concept where I could pull it together and hold it and change this kind of slip distortion type joint to a tighter joint where the joint itself was 125% at a minimum, the strength of any one piece of the beam here. So you can see this untreated steel, you can see untreated beams, and realize that that's what a raw beam looked like for Dillman's. So we took these assemblies and we tested them to check out what was going on. And this is what we want it to look like. And this is kind of what it looked like as we loaded it. So we tested these beams in Flexure to measure their EI values. Hooked up string pots to them, put known loads on them, measured their EI so that we had a good idea of the stiffness of these beams that were really from the same sample set as Dillman. And this is really interesting because it gives us a snapshot of what we're looking at with beam EI. And when we look at E in glulam beams, you look up in your table and you get E value, for example, 11,300 MPa or 1.8 million, for example. The E we typically use in the calculation of our beam capacities, that E is used as a specific criteria. That means it's a rate of deflection for a given load. And we're looking at it from the point of view of what is the deflection in the bridge under a load. That's a specific criteria. There's no safety factor on E. Now, if we have an E situation that can lead to ponding or create additional loads because of deflection, then we go to an E05. And that's the E at the 0.5, the LEL, in the 75% confidence interval. That's a lower E. That gives us a little bit more conservative E. And so we were measuring the E average here to understand the E of the beam to know their stiffness. So why is all this important? Well, I'm going to show you a video here. This is in Dillman's standing up one of the wood welded assembled beams in its 3 segments. As you can see here, it's a tricky procedure with wood because laterally, because wood is anisotropic, it doesn't have the same properties laterally it has vertically. And when you're doing something like this with long, thin spaghetti, you have to be very careful in lifting them. So we lift them carefully and laterally brace them and put them in the bridge in pairs on purpose so that we don't have an unfortunate situation occur. So this is what it looks like before it's received the second girder, because it's going to be matched in pairs with all the lateral blocking in place with the proper wood welds here. And why are we doing it? Well, here's why. You can see they've drawn a string line here along the full length of the beam, and we're looking right here at 8¼ inches from the soffit to the string line. That means that under self-weight, we've reduced the beam's camber to 8¼ Its target original camber was in the range of 10¾ to 11¼ So that camber has been lost. It's the set that goes into the beam and so on. When I take a look at this beam and I look at welding it together, one of the key values in terms of welding is to minimize the loss of camber, as you can see here. So I'm going to just take and start us off here a little bit and go through some basic mechanics. A good friend of mine, Marcia Von Patten, developed this fastener modes, as you can see here, failure modes, many years ago in the 80s. And we were on committee together. And what we always want to do as engineers is understand the dynamics of a connector. And before we get into understanding what an FEM is for a wood weld scenario, I want to just make sure we're all on the same page with lots of important details. So the first thing I want to remind us of is, make this works good, is that wood is anisotropic. You know, what's that mean? It has different properties in different directions. Each direction has a different property, 9 degrees of freedom. And what does that mean? Well, you can have an MOE in compression, an MOE in tension, and an MOE in different orientations of the plane, like RT, radial tangential, or tangential longitudinal. These planes create different values of E. Wood on its own has a modular ratio, N, if I'm talking Doug fir right now, of 1.06. What does that mean? That means it's E of T rather, is greater than its E of C 1.06. Well, that's important if you're going to do FEMs, particularly a wood weld FEM. You need to know where that neutral axis is going to line up with just the beam itself. Now throw into the mix of that, for example, something else, which is the N for reinforcement of wood, that's high strength fiber, and its N as compared to the E of C can be 7, it can be 12. It's what you design it to be in the RP you're using, reinforced polymer. And so anisotropic wood has different properties in different direction. 9 degrees of freedom, 3 types MOE, 3 types of G, that's shear modulus of rigidity, and 3 Poisson ratios. It has 3 directions primarily that its strength are lining in. And if I can do this here, oh, I got to get my drawing skills up here. This is the first time I've used this. Longitudinal, and if I've got a smiley face here, for example, and this is radial here, and this is tangential here. I can have 3 different E's. I have 3 different directions. This is radial and tangential. And so because wood is anisotropic with different properties, it's much different than, say, steel, which is isotropic. Steel is isotropic. Iso. Same properties in all directions. Well, you say, Dan, what does that mean for us with wood? Well, if the wood is different properties in different directions and the steel doesn't, that impacts how we put it together. Wood is geotropic. That means it grows in response to gravity when it's softwood, and phototropic when it's hardwood. Well, these beams for these FEMs we're going to talk about were softwood, Doug fir. So it's geotropic. It grows in response to gravity, generally kind of straight grained. Its specific gravity is about 0.48 to 0.52 untreated. It's about half the density of water. Specific gravity is the ratio of the density of wood to the density of water. It's unitless. We use specific gravity so that everybody around the world understands it. And so if you have a treated Doug fir with copper naphthenate, you might see a treated in the outer zone value for specific gravity of 0.58, maybe 0.6, because copper naphthenate that these beams are treated with is a wall treatment. They're not creosote treated. There's a prohibition against creosote in Nova Scotia. And creosote is a cell lumen treatment. If I've got a lumen, the creosote is filling the lumen. And the density enhancement when I've got a creosote treatment is much greater than the density enhancement when I've got a cell wall treatment, where just the wall itself is getting treated. So this fact about wood, that it's anisotropic, different properties, different directions, that the softwood is geo, that it grows in response to gravity, and slope of grain impacts its strength, slope of grain. So if I've got a piece of lamination that's like this, and it's been sawn out of a tapered, oh boy. If I had a lamination like this, and it's been sawn out of a round tapered tree like this, then the slope of grain that I can have here, this slope of grain is very important. The lower the slope of grain, the greater the strength. Why? Because when you resolve bending stresses and you take a piece here and have bending and it got a load in it, there's bending, you resolve the stresses into longitudinal and perpendicular to grain. And wood strength perpendicular to grain is its weakest strength in a range of 0.1 MPa. So if I've got a knot in the bottom face or a slope of grain issue, and you resolve the bending stresses and tension to perp to grain and longitudinal to grain, the more the slope, the more load goes in tension perp, and this value gets you, and you see premature failure. That's why wood's anisotropic nature and softwood's geotropic nature really impact its capacity. And so this is basics that I want you to really understand, because I'm going to move quickly into talking about why this matters. The third thing that I want to talk about is the fact that wood is hygroscopic. Wood breathes in and out moisture. And when it does, it shrinks and swells. And those 3 factors, characteristics of wood, anisotropic, slope of grain issues, hygroscopicity, they all impact fasteners and connectors and how we join wood together. So just move from there to talking about pilot holes. Now look, traditionally the standards are based on 0.92. That's the ratio of the shank to the pilot hole. It's pH, and this is the shank of the fastener. When that number, when we go below 0.92, we start to see a dramatic drop in the strength of a fastener. When I have 2 pieces of wood and I join them together, boy, oh boy, pardon my drawing capability. And I put a bolt in here and I've joined them together. And I put those pieces in tension. And I got a bolt right here. When I make that pilot hole over a ratio of 0.9, under a ratio of 0.92 by having a big hole and a small bolt, I dramatically reduce the capacity of the fastener, dramatically. The closer I get to one, the stronger the joint. And the current design values for your bolted connections are based on 0.92 or better. Usually this means that we put kind of like 1/8 of an inch on a typical 5/8 to an inch bolt, or 3/16 max. I prefer to run 1/8 max on those bolts. And this business here is what I watch. That bolt hole to bolt shank diameter is critical. And why does this be? Well, if I have a pilot hole and I have the shank of a bolt like this, and he's getting too small so that the ratio is dropping and dropping, when I put a load on him here, what happens is I develop frictional forces here, and that creates cleavage loads. The piece cleaves. And that cleavage load, that basically that separation of the pieces is happening because, what did I say about wood? Its weakest is 0.1 MPa, and that's tension perp to grain. Tension perp. That's the weakest plane of wood. If you take an axe, 2 inclined planes, take kinetic energy by swinging the axe head over your head, bring it down on the end of a piece of wood. The 2 inclined planes take kinetic energy, turn it into perp to grain energy, and you split the cord of wood to burn in your fireplace. You don't want bolt shanks splitting the pilot hole in your bolt group, because that leads to trouble. So that's one of the reasons we don't like sloppy, big, oversized pilot holes in your bolts. So that's important, number one. Number two, when I have a lag screw, there's a difference. The lag screw pilot hole is less than the shank diameter of the lag. And the lag screw as a root diameter, if it's an inner, let's see if I can draw it here. And typical lag screws can be inners or outers. A timber screw typically has the thread root diameter the same as the shank diameter. If you have a cheap Chinese lag screw from China, it can have an inner because they carve it out of a steel dowel. And so if it's inner, you have 2 different pilot hole sizes you should be using. If it's an outer, you can have 1. Lots of self-tapping screws are outers, so you get away from shank friction. And the pilot hole for a softwood is 0.65 to 7.7. The pilot hole for a piece of hardwood, 0.90. Sometimes hardwood like Cape Town ironbark, you have to have 0.95. And that pilot hole allows the shank of the lag screw and its root diameter of the thread, that's over here if I can get it, this root diameter of the thread, and allows the thread to carve into the side of the pilot hole, and an inclined plane goes through the pilot hole, and that gives you withdrawal resistance. When you take a lag screw and you're wanting to figure out how deep to do the pilot hole, you should have a depth to them. You always have the depth of the pilot hole so that the tip of the lag screw can find the pilot hole bottom. So the pilot hole should go to the depth of the shoulder of the lag. You don't over drill them. You have it find the bottom, and then the depth goes from that washer you might use to that shoulder. That's the depth. So using that percent of the root diameter and a 2-stage for inner and a 1-stage for an outer, you create a pilot hole. Now, people ask me, well, Dan, what about torque? Well, one of the biggest mistakes I see today on drawing sets, this is one of the biggest mistakes, do not specify a lag screw without a torque. This is not cooperating today. T-O-R-Q-U-E. You have to have a torque with a lag screw. I've had lag screws where I torque specified as 30 foot-pounds, all the way up to some that I specify 530 foot-pounds. You must have a torque. And never use a lock washer with a lag. You don't want the torque, the lag screw pulling back out. Lock washers are designed to keep the nut firm against the thread in a bolt. And you have 1 lock washer for a bolt group. You don't have lock washers on lag screws, and you always have a torque. Dan, people say to me, Dan, well, how much is the proper foot pounds for a nut and bolt? A nut and bolt foot pound should be 25 as target, 25 foot. What does the 25 do? Breaks the threads. You can have more, but do not impression the washer into the piece of wood. Don't have the nut here on the washer so that the washer's into the wood. You can't do that. It weakens the fastener. Why do people do it? Because they think they can save having to come back and retighten after the wood is seasoned. It doesn't work. You just densify the wood underneath the washer, and it still needs to be retightened after it's seasoned if it's solid sawn. So you don't over torque the bolts. If you want to have a nut and bolt and you want to prevent it from backing off, mar the threads. If you don't want to do that because you want to take it off maybe sometime, epoxy the threads so that it holds the nut on it, and just bring them up smooth, and maybe don't impression the washer on the side. Get it snug, a little squeezed, not a lot. What happens when I take a nut and bolt and over torque it, and I have two pieces of wood that I'm joining here with a nut? What happens is you prevent rotation, and when you prevent rotation, you put side frictional forces on the grain. And where it's rotating, it puts side frictional forces and puts cleavage loads with the nut and bolt group. And your combination is lethal to take and create cleavage loads by undersizing the bolt for the pilot hole and squeezing it too tight to make up for the slop you created when you oversized the pilot hole. And when you did, you create frictional cleavage forces in the piece. You don't want frictional cleavage forces. You don't want an undersized bolt shank. You want to have the proper size bolt shank that as tight as you can. Don't cleave it. You don't want a pilot hole for a bolt, so you got to drive it through with a maul, because that puts cleavage loads in it too. I looked after the Northridge earthquake post-disaster analysis for the Technical Activity Committee for AITC back many years ago in the 90s. And one of the biggest problems in that earthquake for wood wasn't that the wood failed. It performed very well. We had bolt group tear out, what we called shear plugging. And how that happened is you had multiple bolts in these groups, in these cords, in trusses, and in parallel cord trusses. And these bolts, when they got into the earthquake acceleration load, these bolts were undersized. Get this, not oversized, undersized, so that when you got this acceleration load, it created frictional forces. They were over squeezed, over tightened. The washers were impressioned in the wood, and you created cleavage. And this cleavage led to whole bolt groups failing prematurely. These are big features in connectors. So another one of the basic building blocks. I was never taught this in undergraduate. I took 12 years post grade 12, 5 for my FB, another 2 or 3 for my ME, Master of Civil Engineering Structures, and then a Ph.D. in Wood Technology and Structural Engineering in Oregon State. And my whole way through, I went and took all these timber design courses. No one taught me these things. I only found them out through reading and working and designing a lot of structures in my career. And they're important details. My hope is that you all get these details and understand them, because they'll make your connections a lot better. So that's torque, that's lock washers. Now let's talk a little bit about gluing wood, because this is pretty important when you glue wood. I'll get these out of the way. So when I'm gluing wood, I put 2 shoulders. Whoa. What happened there? When I'm gluing wood, I'm taking 2 shoulders and I'm gluing them together. Here you can see, and this glue, this is the 2 shoulders of wood. It's not working nearly as well as it did for me on Monday today, and I'm just not sure why. I take 2 shoulders of wood and I'm going to glue in here between them. And wood glue basically dehydrates to cure. Epoxy glue is 100% solids, and it cross-links together and forms OH welds to the wood. And wood glue has to have 0.004 inches max thickness. Its target is 0.001. Epoxy glue's target is 0.0012 as well, but its maximum is 0.010 inches thick. So that's why in a wood weld, we go to 2-part quick cure epoxy glues that we can get in there, and they'll stand a little bit more thickness intolerance. In a wood product like a glulam beam, the maximum thickness differential in a element, a lam, is 0.02 of an inch side to side. That's based on, that's how this 4 comes around, because if you have 0.02 on the same side of the board, it leads to 0.04. That's your maximum thickness glue line. That's where Lamstock came up with this thickness tolerance. So that glue line pressure does nothing but change the thickness of the glue line. People say, well, the glue's got to be pressured. When you go out and buy a couple of bottles of glue and you're gluing wood together in your shop, you put it in a C-clamp and squeeze the crap out of it. The pressure has nothing to do with the curing, absolutely nothing. All the pressure has to do is close the gap and make the glue line thin. The thinner the glue line, the better the joint. The thinner the glue line, the better the joint. And 96% of all of wood glue's bond strength comes from mechanical. 96% of epoxy type glues comes from chemical. And that 96% chemical that allows you to use a 0.010 tolerance means that you've got to be very careful of the surfaces to not contaminate them and foul them. And you don't want chips in them because that creates a thick glue line. And that's the little lesson on gluing wood. If you're going to FEM and you wood weld, you want to know about gluing because that's critical. And next thing I'll talk about is the open and close time, because open and close time is critical. When you're using epoxy, typically 55 minutes is your open. That's the time you've got to get the surfaces together. 20 minutes is your close time. That's the surface time that's the time you have to squeeze it. And then the cure time is 4 to 6 hours. That's cure time. So that's a little story about the mechanics of making, firstly, mechanical joints, how wood's anisotropic nature is important for it, and how you glue it together, how you leg screw it together, how you bolt it together, and where these design values come from. Now, the next thing I want to talk about is the differences between steel and wood in terms of other properties. Steel has 3 times the coefficient of thermal expansion that wood does. 3 times. The concept of bonding steel, particularly in lengths over a foot, to wood just doesn't work. I can remember the first time at UNB that I made a reinforced beam using steel piano wires. I routed out the wood bottom face, used the steel piano wires because I was chasing a 30 million modulus to enhance the stiffness. Wood's a lot of times governed by stiffness, and the more the reinforcement had for stiffness or MOE, the better enhancement I could get. So I bonded in high strength, high MOE steel piano wires, bonded them into routs on the bottom of the timber piece. The overhead heaters come on in Head Hall in UNB in January, and a 5 to 10 degree change in the temperature blew the joint between the steel piano wire and the wood out. The steel expanded, the wood didn't. It took out the bond line. And when the bond line's gone, plane sections don't remain plane, and you don't have any enhancement from your steel. There's no plane sections remaining plane. So understanding the fact that steel will shrink and expand with changes in temperature, particularly typical changes like we see in the Maritimes of 10, 15, 20 degrees Fahrenheit, will help you to understand why when you wood weld things, steel side plates are not your friend. When you wood weld things, steel side plates are not your friend. So one of the things that goes on with a wood weld is the use of different materials. And so one of the different materials, here's an interesting thing. Aramid, better known as Kevlar or Twaron, Aramid has about the same coefficient of thermal expansion as wood. So here comes a benefit of using FRPs. Is their thermal coefficient of expansion kind of gets the same as wood, and you can tailor design them to be virtually the same as wood. Now, when I bond them to wood, I can create benefit. It moves with the wood. Secondly, if I bond them to wood with unidirectional fiber, no off-axis fiber, and I bond a long piece of it to a piece of wood, if the wood shrinks and expands tangentially or radially, which it does in a range of 3.5 to say 7%, that's from fiber saturation point, which we learned about last week, to zero oven dry, then we can compensate for changes in moisture in the wood, that hygroscopic nature of wood where it shrinks and expands. We compensate by having no fibers off axis, letting the fiber filaments separate, and whilst keeping the tension capacity. One of the great opportunities in using FRPs with wood, tailor them to do what you need to do. Now we make glulam beams at 12 to 15% MC because it's halfway between 0 and FSP. We do it on purpose so they're more dimensionally stable. So engineers out there, don't turn around and pressure treat your glulam beams with water-based preservative and have to turn around and then use them as wet service when you design a new structure. Don't do that. Use oil-based preservatives. Many codes require oil-based preservatives, and we're working hard on 9 and S6 right now. Get those changes across. Don't take a perfectly well-dried engineered wood product and soak it. What's the good of that? Particularly when using something that's water-based, it leaches against the cell wall and will leach back out when it gets water absorbed. So we use oil-based. So then we don't cause it to shrink and swell. We put it in at 12 to 15% and it stays about the same, because we learned last week that the moisture content under an open deck bridge, closed deck bridge, around 14.2% in equilibrium, 16.4% in an open deck bridge. This is in your commentary in C9. I wrote it, I know. And this range of moisture content is about the same as engineered wood, thus it won't change in dimension much. When I use solid sawn wood, which is green and can have 70% moisture content, particularly if it's treated with a water-based treatment, when it comes down below FSP, what happens? FSP is 26 to say 28% MC, it starts to shrink. And so when I've got a new solid sawn green timber bridge, I have to treat it green. When I go back 3 years with a tactile inspection and it's seasoned, I can treat it what? As dry. That's a big improvement. Secondly, what do I have to treat as green? I have to treat my vertical fasteners as green for fastener calculations, because they let water in from the top and keep the area around the fasteners hydrated. That's why we lose longevity with timber. We're either brighten up something that was treated incorrectly or driving verticals into bright from the top, which let moisture in and allow premature failure of the bridge because of fungal decay, which causes 82% of all timber degradation to occur in our connections. So that's another series of facts that are important to have a baseline now for where we're headed. And I'd like to just take a minute right here to stop and answer questions, because I can't imagine there are not questions after this sort of discussion. And then we'll roll right into a wood weld and how we design it. In this particular case, we'll use Dillman's as an example, one that's practically been made for you to be able to go see. So the first question I've got here from Chris Sargent is, 2 of the images on the slides are the same. Answer, which ones are those? 2 of the images are on the same. Yeah, there are. You see them there. That's on the center 2 images. And for the dowel fastener, CSI has holes not less than 1 mil more than 2 mil. For dowel type fasteners, CSA 086 has holes not less than 1 millimeter and more than 2 millimeter, and NDS has 1/32 or larger bolt end, but code something for future codes. Same as the torque loads, existing codes. I understand. So what Chris is asking is, he's saying he's citing both CSA and NDS in terms of the oversize of the bolts. The current design values for NDS, for example, and for 086 for bolted connections is based on 0.92. The 32nd and 16th that we see used, you see that number here, those numbers are to allow opportunity for the mechanical characteristics to be about where they should be and people to field dress it to be able to install it. I'm just getting inside the code a little bit more for you to help you understand the basis for where the numbers came from. That's what I'm up to. Now, those numbers, a 32nd to a 16th, are going to be fine. You're not going to have that much difference. If all of a sudden, because I had 4 pieces of wood I wanted to bolt together, and the guy didn't want to have a welded long shank on his auger to form the pilot hole, he's got a short one, and he's drilling from each side instead of having a long one he can go all the way through with, guess what? They oversize them by their 3/16. I've seen them a 1/4 of an inch on a 3/4 inch bolt shank. They are dropping in strength dramatically in terms of their capacity. What do they do to compensate? They over torque the crap out of them. They put a air torque gun, which will run about 90 to 100 foot-pounds, and watch those washers, big flat ones, seize right up to the wood. And people say to me, Dan, well, they called me one time. They said, I've got these timber washers. They're all cracking. I said, well, stop over torquing them. They're designed to crack. You don't want to put a lot of torque on your nut and bolt. That's what timber washers are good for. They're cast and they crack when you try to put too much load on them. It's a safety. But you can buy thick, big 3-inch washers that are thick stainless steel or galvanized steel and really impression those washers. You do yourself a disservice. And Dillman's is located close to Meagher's Grant in Nova Scotia on Wise Road across the Musquodoboit River. What other questions? Any others? I can't imagine it. We're going to be moving after this code cycle in 9. I'm really going to be encouraging committee to move into this whole area of connections because it's one of the great mysteries. And it's such a critical part of timber bridge work today. Okay, so would you please remind me? Okay, that's got that one. And okay, I've got that one. Got that one. Okay, good. Okay, dismissed. Okay, good. Okay, we're going to move on. So now we're going to get into this thing called the FEM connection at Dillman's. This is an example I wanted to use for you. It's underway right now and it's relevant and it tells a story. So these are the pieces that were pre-machined and pre-assembled at the plant. Then they were taken apart. The steel was sent out for galvanizing and the wood was sent out for treatment. And we spec'd copper naphthenate with 0.07 pounds per cubic foot of reactive agent. It was carried in a number 2 diesel fuel as a solvent, heavy, and it was loaded up. And we treated it and measured its depth of penetration as per 0.80 and its volume of uptake penetration. And its specific gravity did not reach 0.74 to 0.78. Believe me when I tell you that. It's not published. That's not the right number. So the number it might have reached is 0.58 to 0.62. So you can see here the piece, this is the end piece. There's 3 pieces forming one beam. And we're going to go from a mechanical type connection with a slip distortion factor that you could calculate as per NDS, not as per 0.86 and C9 of S6. We're going to go from this type of connection to a wood weld connection where we have no slip. And this joint is 125% of any place in the beam. So first thing we're going to do is we're going to plane down this surface and get solvents and any residual contaminants off the face where we're going to apply RP. And why are we doing this? Well, I said to you earlier that chemical glues allow us a little more flexibility and thickness of glue line up to a 0.010 of an inch. And when they have one Achilles heel, and that's contaminants. So you can't have oily, slick surfaces and bond to the wood. It wants to put an OH weld onto the wall, the cell wall, hemicellulose and cellulose, and it only can do that if it's not got an interfacial contaminant. So we plane the surface. You never sand wood to join it. You can use big sander, abrasion sander, drum sanders in furniture making and evacuate the dust so that it doesn't fill the pores. But out on the site, you don't sand wood to bond to it. You always plane and join it. And that way the pores don't fill up with dust. They get evacuated. Why is that? Well, we want all the possible opportunity for any migration, even from the large molecular weight, 100% solids chemical type glues. We want any migration we can get. If we're plugging the pores up with dust, that isn't going to happen. So the other thing we're going to do is recut these guys because they could have got contaminated in there with solvent because we're going to glue in here now. So we're going to open them up, kind of reroute them a bit, reroute the faces, and we're going to plane the faces and get them prepared. You can see here what's going on. We got our shear plates around. We've got steel. Notice something about the steel. The steel is wrapped in saran wrap. Why am I wrapping that steel in saran wrap? Well, the reason I'm wrapping it in saran wrap is I don't want that steel to get bonded to the wood. That steel's there for a mechanical connection, not a wood weld. And if I bond that steel to wood, within about 3 seasons, I'm not going to have a wood weld, because that steel is going to shrink and expand with moisture change and blow the joint out, and it's not going to be bonded anyway. So don't bond it. And to protect the bond from happening, saran wrap it. Create an interfacial. Plane the faces where we're going to bond them together and reroute these pieces to get them right. Now, what are these connections doing right here? Look at these guys right here. They're a thrust rod kit. And what they're going to do is allow us to apply, take a nut and a threaded rod and attach the nut and threaded rod through these 2 holes and pull the beams together. And we want to create 125 PSI, which is a typical bond pressure, to close the gap. And this face has to be remachined to make sure that it's smooth and even, so that when we pull it together, we get a thin bond line. Now, can you bond the ends of wood? A lot of people pick me up in this course and they say, Dan, I was taught that you never could bond the end of a piece of wood. Well, it's true that 100 grain end grain travel of moisture is 100 times faster inside. Yes, that's true. And if it was wood type glue, that wood glue with the solids would immediately dehydrate into the open pores and leave the glue line starved. Yes, that's true. But we're using a chemical type glue, 100% solids with big molecular weight. It gets 96% of its capacity from a chemical bond. It doesn't migrate. And yes, it could migrate some into the open pores, but we're going to spread it at a spread rate that's important to allow us to have squeeze out to assure ourselves that we got ample glue in there to find that glue line. And that we're going to create the thickness in the glue line that we need to create that joint. Now, is all of the wood weld coming from that glue on that butt face? No, no, there's no way it's coming. There's a composite of shear plate and dowels, you're going to see here in a minute, and glue, side plates, shear panels. There's 5 or 6 ways we're bonding this wood together to come up with the total V that we need at that point, and the total M resisting moment couple that we need at that point. That's where we're headed. So you can see here, we planed down this face and we're into these routes here. We've opened them up a bit. We've got 2 of them on. You can see this placement here. This is the RP. These beams, all 3 segments, are reinforced with high strength fiber. And we also have to bond the reinforcement together at that FEM. Here you can see the shear plates that were going on the butt-to-butt face, and a hole in here for the dowels that go in. And this is the shear plates on the side face. We've got compression plates as well for lateral stability. And we've basically got this piece to a spot where we're getting ready with our steel and our nuts and bolts. And we've talked about how much torque we put on a nut. Now, I talked about this torque on a nut for a reason, because in this particular case, we're going to over torque the nut. Now, people say to me, Dan, do I need to have a washer on a face of a steel? See this right here? See that? There's a washer there. We don't need a washer on a steel plate, but this washer is serving another function. What are we up to here? We're trying to create the pressure to get this squeeze out. See the squeeze out here? And why is the squeeze out more here? Because we put a lot of glue around this shear plate because we want to glue that route. And what are we up to? We're up to creating a rigid shoulder in those shear plates. So here we go. Look at the epoxy. We fill in the gap that's around the route and the shear plate edge. See it here? We're creating a glued face and a glued in place around the shoulder. And what are we doing? When that glue cures, it'll quickly cure over. We've got a shoulder to shoulder and a hole to hole ratio for the shear plate and the route of 1. That's what we want, 1. Because if I have 1, then I'm going to have minimal slip distortion. And if I can get 1 everywhere, I'll get a better wood weld. If I just put this without epoxy, we'll have slip distortion and we'll get some loss of planned on camber because this will run up against the shoulders everywhere. And when it does that, it lets this joint open up a bit, and it costs us deflection out of our camber. So you can see the dowel. So we calculate, we're going to go through these calculations in a bit. But you can see the dowel here. It was pre-made. It was specially made for this shear plate with a perfect fit hole so that we didn't have slip. You're getting a lot of pictures and a lot of verbiage. And believe me, there's a whole lot more detail in all this. But in a 2-hour session, I can't get into all the details because there's a lot of things going on in these pictures. Believe me when I say it. So you can see here, we got the dowels in place. We've got it lathered up with epoxy. We're ready to make the first step of this, which is to take and use these guys here to create this thrust rod pull. And you can see this glue in here. See the glue in here? Look. Look at the glue. The glue. The glue. And here's a thrust rod engaged. And what did he do? Here he is here. Look at this thrust rod engaged. He's engaged. You can see this guy here is on. This guy's loose, but this guy that's not here is engaged. And what he did is we basically used these thrust rods to create this butt-to-butt pressure and cause the squeeze. And you can see the squeeze out here. And that's leading to a tight glue line, a thin glue line. And here's the RP coming close together as well. RP and RP, planed up face, the thrust rod engaged, squeeze out. That's our step one, to create 125 PSI, properly infill the routes and get the shear plates and the dowels engaged, and pull this together with this butt-to-butt part of the FEM, fully engaged and glued to face so that it's got little or no slip distortion. And the next part of this is, how do we get this unidirectional RP? Well, you can see this is aramid. It's an aramid glass mix. Glass alone is not a good thing to use on a bridge because it has 92% fall down for fatigue. Glass, when it gets combined with moisture, particularly some salt air moisture, and you repeated load it, it has a really big fatigue. And you have to use the 92% of your ultimate and then factor that by 1.3 for safety. And so I combine it with aramid to keep its strength up, because aramid has great tenacity, is great cyclic resistance, and it's just a great man-made fiber all around. And so when it's unidirectional, I put this picture here on purpose. This is a knife edge. We can take a big roll, 2,000 feet of it, 50 thousandths of an inch thick or 70, depending on the design, and literally pull it through that and make our strips. And here are all the strips for the FEMs, all pulled out of bigger product, unidirectional. What's its capacity? The strength of this in tension is 5 times the strength of steel. 5 times the strength of steel. Its E is lower, but its strength is much higher, and it's at 1/5 the dead weight. And you see the pieces here ready to go. And this is the thrust rod assembly with the piece of reinforcement underneath it on the tension face, because we took advantage of this to put in a piece of tension reinforcement here on the side with this wood weld. So you can see it's wrapped here with saran wrap. It's bolted through, and I'm going to come back to this. We had 315 foot-pounds of torque on these nuts. That was a calculated amount to create 125 PSI in bearing, parallel to grain. These guys, instead of having the traditional 25 foot-pounds, had much, much higher torque values. Why? Because we were using them to glue. That's why we used a washer as well, because in addition to attaching them to the beam, we used them to glue RP to the beam. As you can see here, the holes in this beam are this hole. You have to calculate the net section here as part of your calculation of the tensile capacity. And you've got these guys wrapped here in saran wrap so they don't bond. If I put this steel on this guy and used a lot of glue, the glue would wick out and come out the edge and get attached to it, and I'd bond this steel to it. That would be bad. We don't want that. We want the steel to be able to shrink and expand with thermal change and not impact this RP, which sticks with wood, because there's where we're chasing in a wood weld. We don't want slip distortion. We want to eliminate slip distortion, make that wood weld 125% of the wood, and we go to every precaution to do it. Notice also the surface of this RP. It's not sanded. This is not a bondable surface. We have zinc steroid that gets a film on the surface and makes it nearly impossible to bond to it unless you prepare the fiber just before bonding. Let's see if this plays here. You can see them going on it. This is lifting up from that plastic. You can see it. It's got the glue on it, the sanded face, and it's lifting up from the plastic. It's basically not going to bond to it. So you can see here, this is the pieces of this is both halves of the FEM. This is the compression side. These tabs are to join the deck panel at this point, because the routes here for the S-clip, which we'll talk about later on today or next session, is it serves a purpose. So when you have these up here, you don't have the routes, so you have to mechanically join the deck to this FEM. You can see this is the tension side. We don't put the RP up in the tension face because this is a butt-to-butt joint here with this close proximity butt-to-butt connection, as you can see here. And this is a completed one. So we've installed the shear plates, we've installed the retro bond. We basically had a 3 or 4 step process. There's more steps than that for the workers, but for this course right now, suffice it to say, the first thing we do is prepare the butt-to-butt. We get the reroute, the reface, we get the dowels and the shear, we install the epoxy. We then use the thrust rods to pull it together with 125 PSI. It cures. Then the next stages of this journey are to place the steel down with the RP between it and the wood, sandwich it to glue it to the RP. We infill those shear plates as well to keep them from having slip distortion. And that's got basically the side assemblies of our connection. This is the top compression side of the beam. Top compression side of the beam. You can see all the different assembly elements. Now this is the bottom side. This is where the tension reinforcement bonds to the tension reinforcement. This is a very complex joint, for good reason. In a reinforced beam, the high strength fiber that's on the bottom of these beams doubles the moment capacity. In some cases, it triples it, depends on the design. If I'm going to triple the moment capacity, you got to know there's a lot of stress in this RP. People have tried this for years to do a simple transform section analysis and calculate the shear stress at the RP wood interface. And believe me when I tell you, I've tested a ton of big beams with shear rosettes all over the place to understand that it isn't VQ over IT in a transform section, in case you're wondering online. There is a huge amount of shear that develops in here in this interface, and this RP is carrying a lot of load. And if I'm going to join these two pieces together, I want to be good and sure that I got a good connection. So what I've got here is a long length double layer of FRP cover plate. And I'm going to prepare this surface, use epoxy, spread on both, and join these two ends by putting this RP in here. And I've got a whole regime of lag screws that I'm using in this area. You can see in here, and I put a steel cover plate over, and notice that I've got this, saran wrap, keeping any gluing from taking place between the steel plate, the RP, and the wood. If you're gluing steel plates this long to wood, you're going to be sorely disappointed. And even more disappointed is going to be your buddies who bought the bridge. Because when the wood sucks up and lets out water and it shrinks and expands, plane sections won't remain plane, and it isn't happening. And so if you want to take this mechanical bond that's not a wood weld and move it to a wood weld, you have to have other things going on in order to achieve that purpose. And this, as you can see, is a completed one here. At 24 hours, it's cured 92% in 4 to 6. But we let it go at 24 before handling it much. Any questions here about this process before I go on to the next part of this? So the one here from Chris, it seems like you're the one paying attention, Chris. There's got to be other people listening, I know it. So is the capacity of the FEM, say on the tension side, only from the fiber and the steel plate only for glued joint? Steel plate is left on for redundancy? Okay, here's the answer to that. So two or three roles the steel plate is serving. Number one, if I didn't want a wood weld and I wanted a purely mechanical joint with slip distortion, is not provided for in the Canadian code, is an NDS under the group factor. If I wanted to cut back on slip distortion, I move to the wood weld concept. If I don't care and I'm prepared to accept it, along with some what I would call serviceability issues because it moves more, blah, 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 then I could stay purely mechanical and use the steel plates in this assembly only. Chris, you saw in the earlier slides where this steel assembly only without the RP and all the glue was carrying at L120, that's the length over 120 in deflection, was carrying 100 tons. So it can get the job done, but I'm talking about going a step further. I want serviceability issues settled. I don't want to have a gap, recreating a gap every time a truck goes over. I don't want to lose the original camber too much. I want to hold soffit height high. I don't want the working of the joint. So I'm moving to what I would call a weld type joint. And this is an external one. For another course and another time, if MLB has me on, I'll show you an interior FEM where there's a wood weld and we have no slip distortion for buildings where I have architectural grade beams. But I think we have to walk before we run, and this is the first way I'm going on it. So I could leave the steel there, or I could take it away. I'm leaving it because why take it off and spend the money? It's good redundancy and so on. And I've got no fixture of it to the RP or the wood because it's saran wrapped. I'll cut off that saran wrap because it'll blow in the wind and look like hell in a few years. So just cut it off with an X-Acto knife where you can see it. Any other questions?
Yeah, Kenny's got one here. I'll allow him to speak.
Okay, Ken, go for it.
Yeah, just in terms of the preservative treatment and the oil-based, how is that impacted, or how does the glue that's used in the laminations, how is that impacted? Because if
Ken, it's an excellent question, Ken. If this was a cell lumen treatment like creosote, we could still glue it. And what we do, Ken, just before the glue is applied, you plane it, and just before the glue is spread, you tack cloth it. And what you're really looking to do there is expose cell wall. Because the bond that occurs with the two-part epoxy system is an OH weld. There's OH hydroxyl groups that bond to the hemicellulose on the cell wall, and that's where you're getting your capacity. So if I get the contaminant away from it by tack clothing it just prior to applying, then I get where I'm going. Does that answer your question?
Almost. It was more about the base material, the glue lam beams. Does the glue that's laminating those individual pieces, does that affect the uptake of the treatment?
You were talking about the phenolic type wood-based glue, which is 51% solids. I understand you. So when I make a glue lam beam and I'm laminating the wood pieces together, I always want wet serviceability, and people don't know what that means. They think wet service as in decay. That isn't what it means. It means we test it in cyclic delam. We soak it, dry it, and check for delam. And what happens to cause delam is weakness and tension perp in the glue line. And so that's wood's weakest way. That's what causes delam is tension perp. And so the wider the beam, the more subject it is to cyclic delam. So when we make a wood beam, we like to use a thermoset glue. That's a one-way glue that doesn't go both ways. It doesn't soften under moisture. Number two, 51% solids, or 50 or 49, means it dehydrates to cure. The water travels into the wood 3/16 of an inch, about 80 to 90 angstroms, and it goes in there carrying the smaller molecules, because wood glues have different size molecules, and when they polymerize together, go from monomers to polymers, they link with the smallest, deepest in the wood through the biggest in the glue line itself, and then the other way, the other side of the glue line. Well, the treatment itself penetrates a glue lam beam laterally. So in other words, it's going into laminations that have been incised, and these incisings open up end grain, and then it penetrates through these pores if it's not got aspirated pits like it does in inland dug fir. Inland dug fir does not treat well compared to coastal. I always spec coastal. And when I'm testing tactile stuff in situ, I always look to see if it's coastal when I take cores and put them under a microscope. So this aspirated pit issue is a factor. But you're asking the question, will the treatment migrate across the glue line into the next lamination? That isn't how it works when you've got it in a retort, as you know. It's going radially into the wood from the bottom and side faces. It's going sideways into the wood. End grain travel of the treatment is big. It's in there 6 inches sometimes or more. But on the side, it's going in 1 inch to 1.5 inches. So it doesn't cross the glue line. If I had a glue line, say I had two-way gluing, and I was two-way glued glue lam beam with narrow laminations widthwise glued in a vertical joint, and I used a species that's treatable, like spruce isn't treatable, So I was going to be treating it. So it was coastal Doug fir. And I glued it with two-way gluing. The treatment is dramatically hindered by those vertical glue lines. Did that answer your question?
Yes, and I have additional questions based on that.
Okay.
Are there engineered wood products like Paralam that are not treatable, or does the like are there?
Yep.
You're dealing solely with solid sawn timbers.
Well, solid
laminated-
sawn or solid sawn to the extent it's a lamination and a glue lam beam. LVL doesn't treat well.
No, okay. So
Exactly. Paralam doesn't treat well. It's too high a concentration of internal bonding agents.
okay, that's good. That's what I was looking for. But
yeah,
yes, your question did answer it. I was concerned that maybe if there was delamination at that glue line, but it sounds like that is not the issue because of the phenolic glue that
Yeah.
we're using and
Right.
the method of penetrating, or the
Right.
method of treatment. So
It's funny, Ken, you're talking about this. I handled the big pulp and paper plant here 12 years ago. It was a huge contract to deal with the big main carry beams. They were 72 feet long, 5 feet deep, and 12 inches wide. And they're made all L1D, L1 dense, not coastal. This is L1D because they weren't treated. They were inside. And they were made with casein glue, the old animal blood glue. It's an organic glue, and it's not wet service. Glues are either wet service or not wet service. And the glue lam beam was so badly delammed, its average shear value was 21 PSI, when it should have been 1130. And you could literally pick the 2x12s up with your hands like a deck of cards. Bang, pick them up one at a time. The glue had just kind of dissolved and gone away. And you're left with a stack of laminations with no bond between them. And so when you're building a bridge, wet service is critical. People say, well, Dan, I'm going to use, I'll use a polyurethane glue, PU. It's expandable foam. It turns the time and the lockup a lot shorter. It's a foaming agent, which pre-polymerizes. And one of the hallmarks of a polyurethane glue is it tends to have less penetration. If you take a regular phenolic glue, it's penetrating 3/16 of an inch. A polyurethane glue is penetrating maybe 1/8 to 1/16. And therein lies the devil in the details. And that's a big issue, because if you take CLT and try to make a deck from it for a bridge, it'll delam all over the place. Currently, most of them are made with polyurethane, some with resorcinol, but you've got too much of a difference between longitudinal and radial tangential shrinkage and expansion. And trying to hold those together in a deck panel is a bad idea. It just doesn't work. And what they do with LVL to make deck panels out of it is they put the cross banding over 5 or 6 lam veneers. And again, you've got so much glue in the glue lines there. If you use even a phenolic to do it so that it won't delam, your penetration of the preservative is pretty shallow. So there's some inherent issues in there that you have to deal with when you're thinking about serviceability. The Nova Scotia government doesn't want to think about these laminated beams delamming. So what I always specify is a second round of third-party work where we do another round of cyclic delam test. We have full soak, dry it in an oven back to 15% of original weight, check for delam. And they're supposed to do it when they make the glue lam. And so those two tests make sure that we simulate. One round of cyclic delam testing simulates 10 years of service. And so that over that time, we're figuring on moisture cycling. And that's really, really important in a bridge, and it's really, really important in an FEM. Any more questions? I see one up here, Dave. Have I got another one? Hey, Bob's saying to me, would you ever consider removing steel? You just answered. Thanks, Bob. I just leave it. What's the sense? You pay money to take it off. The labor is not worth it. Just leave it there for redundancy, and it's there. It's galvanized. It's going to stay there, and blah, blah, blah. Other questions? Okay, we're going to keep going. So now we've got this tension splice on the bottom face. We put 2 layers RP. We've used the legs and the plate to get them where we're going and get them attached. Notice something about those lag screw heads. There's no lock washers on them. And we're using the plate as the washer, and we're basically snugging them up with a known torque. And they have a specified torque. And in this place, we target to take these legs when we're bonding the RP to it to around 215. If they're deeper and longer, it can go as high as 320. The torque is driven by what? What does the torque do? When you have a leg screw, Its difference from a bolt is that the inclined plane of the thread twists through the shoulder of the pilot hole, creating withdrawal resistance. Well, that's how a lag screw is different from a bolt. A bolt doesn't create withdrawal resistance. If you put a nut and a washer on the other end of it, it can, but that's not its function. Its function is to provide for lateral, either lateral perpendicular or lateral parallelogram or what have you, capacity. The lag has got one of its key features is its withdrawal resistance. So I take this lag screw and I give it withdrawal resistance by having a pilot hole at 0.7 its root diameter if it's an inner, or with two-step, or 0.7 of its shank if it's an outer. And I take this lag screw and I torque it in there with a known torque, let's say 315 foot-pounds, and that is creating withdrawal. Well, the opposite of withdrawal is pressure on the plate to squeeze the glue line. And the number of lags we use and the torque we use and the length of the lag and the size of the lag are all engineered components of creating a thin glue line. Yes, they also serve a purpose here in providing longitudinal and lateral resistance at their shank for the capacity of the joint, but their dual purpose here is to cause this right here. You'll see it. That squeeze out. That's going to give us a thin glue line. And we want thin. We don't want more than 0.010 of an inch. So let's get into what this demand looks like. Well, I had the engineers cough this stuff up for me, so I got cut and pasted in here for you. And what we're looking for, and this girder at this, what one governs. Remember, we staggered the splices for redundancy. So one had more shear than the other, and the other had more moment than the other. So we took the maximum of each, and we're just going to design one FEM for all of them. So we don't have different FEMs. That makes for screw ups in the site. And we got 2,807 kilonewton meters in moment and 322 vertical shear at that point. So we're going to go through and take these factored loads and some unfactored forces due to the FIRP side, because the reinforcement uses ASD, as most of the American side still does today with bridges, because their national design standard and others are kind of still embraced in ASD. So we kind of walk between LSD and ASD around the world in different bridges I use. So I just get used to using both. And our engineers get used to using both because we go back and forth. And so we are going to determine the total capacity and compression. Well, there's some really interesting things here, because we know intuitively that the butt-to-butt connection and compression is going to give us a bunch. But yet we have to have the side plates on the compression side for lateral stability too, and for shear. That's that lateral resistance. So I needed the shear, and I needed some stability laterally for the beam itself against nosing loads or hunting loads when the wheel of the truck going across moves a little bit side to side, puts laterals on. Let's say in the railway business, Bob knows this, a 16th alive, for example, on trusses, or on a trestle in a 12 to 15 foot span, you might have 25,000 pounds of lateral put on the cap. And so these lateral loads, even though there's no debris field here because the soffit height is above the 100-year return, we've got an opportunity still to have some of these lateral forces. So the side plates on the compression side are going to serve the purpose of providing lateral stability, vertical shear capacity, holding the piece together under loads that move up and down. There's not going to be a reversal of moment, but you can have moment go from highs to lows, and that moves the beam up and down. Why I like this chemical type weld that we're talking about in this particular butt-to-butt connection. So as you can see here, we're basically determining the total capacity and tension. Now, the tension side is below the neutral axis. Well, how do we calculate that neutral axis? If Wood's own modular ratio is 1.06 for Doug fir, and we're going to have a piece of high strength fiber on the bottom of it that tends to pull the neutral axis down, we're going to have to calculate the rotation of this FEM to determine moment arms for each of the compressive lines up top and each of the tension lines at the bottom, because their distance from the neutral axis will determine what share of the resisting moment couple they take. So you've got a share in the resisting moment couple governed by the placement of these rows of shear plates, and the placement of the steel plates and the placement of the tension splice of RP in the bottom face, for example. And all of this has to work in conjunction together. So this shows you here the different placement of the rows and its different positioning and the center of rotation in the splice plate connection, as you can see here, as you can see where we've been designing this value here. And you can see the numbers here in compression, the numbers in tension in this bottom of the beam, and the distribution the same. The distribution of the demand load, this lateral resistance of a pair of shear plates, becomes around 85 kilonewtons. The compression resistance of the butt to butt around 1447. Now keep in mind that this, I'm going to use my pen here if I can get my hands to work right. Who knows? Boo. What? Okay. Now, most people look at an MC over I, and that's what they think. If you look at a piece of wood and you look at it in bending and you consider its own modular ratio, the wood itself might, let me get to where I am here. This is really going to be a thing. So the wood itself might create a modular ratio that reduces the neutral axis. As I put this wood, if I put piece of reinforcement on the bottom, if I put the piece of reinforcement on the bottom here, and I put this beam into a lot of load, what ends up happening is the neutral axis ends up dropping. And over a process of time, the neutral axis drops again and again, and you get a big stress down here in tension. And Garfunkel was the first guy to look at this modular ratio with wood. And when I got started in reinforcement back in the 80s, I started testing and strain gauging beams a bunch and trying to find out where neutral axis is, what happened to shear stress across the width of a beam, across the depth of a beam. Was it true that VQ over IT, is it true that VQ over IT, which in a parametric section converts to 3/2 VA, was it true in a glulam beam with a piece of high strength fiber on it? Could I predict the shear stress at a point by simply going to 3/2 VA in a transform section where I transform this I and come up with a composite I? What did it look like? Well, I soon found out through a lot of strain gauge testing, it didn't look at all like I thought it was going to look like. And also found out some interesting things, and that is that shear at reaction points is already at 4/2 VA in a simple span, and that it's a maximum at the bottom of a reaction point. It's mushroom shape like this, a max at the bottom. And so I had to be very careful where the shear stress migrated in the design of a wood weld, because I didn't want to have the shear stress greater in certain areas than it was in others. I didn't want to have the moment stress that I was calculating to be different and its MC over I to be different. And so what I was really looking for here was to understand this distribution here. If I take a glulam beam and I look at its load deflection curve and I look at just the beam itself, it typically, no. It goes like this. And I got YP up here. Traditional design values with wood use this kind of percentage of the curve. When I put a piece of high strength fiber on the bottom of the beam and shut down localized defects from causing global failure due to localized tension failures, then I can climb up that curve a bunch with my value and use this portion of the curve like steel does with plastic design for my safety. And I can get a much higher value. So I'm operating up this portion of the curve with high strength fiber reinforced beams. giving me 2x for moment capacity, because I'm using this guy up here, shutting down localized failures in tension on the bottom face at slope of grain around knots or other localized defects, having the RP transition stress by. And so I developed this over here, if I can draw it over here. I developed this sort of boxed in analysis that looked a lot like a crack section design in concrete. The difference between this, what we call compression-based design in timber, and concrete is that in concrete, when I reach the yield point, it goes away. With wood, when I reach the yield point, it stays in service, and thus will allow it to block in a lot better and look more like a typical concrete crack section design. The difference being is the wood in tension has some value which concrete doesn't. So in a compression-based reinforced glulam beam design, which my design methodology is now covered in AASHTO, if some people want to go look after, they used mine to develop the AASHTO value or formulation. If you look at this, you'll see here, this guy blocks. This guy does this, and the RP is getting a lot of stress. That's how we're doubling moment capacity or tripling moment capacity, depending on the design. So that's a little lesson in M and V for glulam beams. What's it meaning here? Well, obviously, if I'm not thinking about these things, I got some real potential trouble for myself at this wood weld where I don't want slip distortion. I want a tight joint with 125% of capacity, and I want to get the loads through that joint. So here we go, back to this topic at hand. How did I allocate the capacity of each of these lines of compression, resistance and tension rather, and lines of this one here is my thrust rod, and then these guys up here on the lines of compression splices. I got compression splices, I got my thrust rod, I got my thrust rod. Upstairs, the thrust rod is putting compression on the joint, so it actually superimposes on the compression created by moment. Down here, I'm putting this guy into compression with a tension force here, and he's kind of, in a sense, canceling the tension force because he's in compression here to create the joint. So I got this going on, I got this going on, I got this going on, and I got these 3 or 4 or 5 lines. And each of these guys have a weighted relationship with the neutral axis to form a resisting moment couple at that point. If I put the same allocation as capacity here, that's not going to be too good. If I just calculate the capacity right here and say that's what it's going to contribute to the resisting moment couple, I can be sorely disappointed because of its relationship with the neutral axis. So I have to relate those things, those lines of action, to the neutral axis and to the applied demand moment to form my resisting moment. So this is a short, quick calculation. You can see here, I put in the references for you. You guys can get access to this, I think, through Dave. You can take a look at what we come up with for the resistance factor for limit states. The resistance perp to grain, 35 kilonewtons, that's just straight coming out of the table. The group factor, watch out for this guy. This guy here can have a slip deformation over an NDS and not in Canada. We don't have it in Canada in 086. We don't have its proprietary, most proprietary connections for, FEMs that are no slip distortion. And you don't have it in C9 for sure. They're a long way from having it in C9, and it's just not there in 086. So over in NDS, you can see some more information on that. So you've got your JC, your JT, you can all these table of reference, your fastener row factor, the number of rows, blah, 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 all the way down here. You can see here the lateral strength resistance connection parallel to grain, and your factored lateral strength resistance parallel perpendicular to grain, and your demand shear. And so it checks out. The utilization ratio is 0.99. Well, you know what? The first dozen times it didn't look like that. You're just seeing the final result. Guess what? So, if you've all done design before, you know what I mean. You have to figure around with it to get it to work. So that determines your spacing. There's a geometry here from spacing your dowels. There's a geometry in spacing these guys on the sides. So there's geometric features that are governed by code for the spacing. The size and placement of these are governed by code placements. You can see here this 2-part pilot hole here because they were inners. You can see it here. And the side plates out here. And these are the dowels. They were a special shear pin that was produced just for this effort. You can see the size here that was produced to get close to the shear plate as we cut down the whole business of slip distortion. This is the butt-to-butt shear pin connection here. You can see this number. This is a factored shear resistance to 821. The demand shear resistance 322. Okay, it's got a great utilization ratio. There's a lot of capacity in there. I've just loaded up that butt. I figured if we're going to make it, let it go by geometry. And so back in here to this guy right here, you can tell basically we're looking at this lag screw design here, the resistance factor. This is at that bottom plate with a steel plate. Sorry. And you can see these factors: a nominal diameter lag screw. We used a 1-incher. The number of fasteners is calculating the individual value. The number of shear planes, 1. This is a lag yield strength. This is a load distribution factor. The service factor is 1. We're considering it dry. Remember, it's glulam. We're going to have it under a tight deck and it's going to stay dry. And these don't have a vertical that originates from the top, only from the bottom. And we have mostly horizontals. Treatment factor, adjustment factor, thickness of the side plate, length of penetration. You can see all these, you can calculate themselves. We're not going to drag this out because I only got 2 hours. So the governing unit lateral strength here, you can see it 39.4. This is the factored lateral. And you can see the capacity here, the steel side plates. I want to get rid of that. Get rid of that. So you can see here, factored steel, minimum tensile strength, embedment strength, side member, mean relative density, 0.49. We used 0.49, could have been a little higher because it's treated, and Doug first 0.48, 0.52. We're a little on the conservative side for that. But I don't like to see density increased for treatment because most of our fasteners go all the way through the piece, and the treatment is an outside zone. And embedment strength of the main wood member, you can see it here at 18.3. So this provided for us to come up with the maximum factored forces, of course, and the moment couple forces on the side plate, as you can see here. Sorry, this keeps getting in the way. Get it out of here. This is the tension applied to row 1, 2, and 3. And as you can see here, that this is the tension in 1, 2, and 3 coming out to this tension. This is a minimum tension resistance here, tension resistance here. And what we're basically showing is that with the allocation of the loads via the moment arm off of the neutral axis, is that every allocation of load, that row meets or exceeds its capacity. Now, what did I mean by that? Well, one way to design this is to change the number of shear plates at each location based on its weighted share of a resisting moment couple. I don't like having connectors that have a bunch of different things going on. I like connectors that are the same. So we designed for the worst case FEM. We designed for the worst case side plates and bottom tension splice. I want everything the same. When the crew set up to do 8 girders, 2 FEMs per girder, the first one took them 3 times as long as the last one. And so if you change them all the time, that's where errors go on. And so you can be penny wise and pound foolish. So what I was really chasing was, what is my capacity in a line? Make sure that the capacity in a line is more than any one line of demand in its relationship to the neutral axis. And from there, just make them the same. This is the bottom plate design here. You can see this relationship. This is the bottom plate design is the furthest away from the neutral axis. It can potentially carry the most load. Thus why I govern the length of the plate steel by the RP. In order to gain redundancy, because I like redundancy and I like extra capacity, particularly in FEMs, I designed this joint so that that bottom double RP layer had enough development length when it's adhered to the RP on the pieces, the 2 pieces, it had enough development length that it could develop in shear all the tensile load needed to maximize the tension in the RP. When the tension's maximized in the RP, the rest is redundant. But I want to form up a joint that's got stability, both laterally, vertically, moment, shear. I don't want a weak-kneed joint that's only good in one-way bending. And secondly, I want a wood weld that's got 125% capacity of the beam. So I like these redundancies. I like redundancies that involve an RP getting glued to the faces of things where there's no slip and carrying the load. So you can see it here. The length of the RP develops sufficient shear capacity to translate tension. And as you can see, this is ARP. This is shear strength here in 390 PSI. Now these values that we're seeing here are, for RP can be bolt shank, which in ASD, for example, in a bolt shank is around 1100 PSI on a thin piece. Or if you're talking about shear in terms of its design next to the wood, it can be 390. This number is usually governed by the wood, because when I attach piece RP to wood, it's really only got the strength of one shoulder, which is the wood. The wood is the weakest member. So that's where the 390 comes from. That's a proprietary number that comes out of code approval for RP 6046. You can see it here. And this is again in LSD. We took an ASD value 290 to 320, multiplied it by the upside for LSD, and that's where this number came from for the wood. The LRD format, this is resistance factor, blah, blah, blah. Resistance, low duration system. This is low duration relevant to reinforced glulam. This is highway traffic is a 1.15 because it's not permanent. It's getting across the bridge, and we assume 10 years of cumulative load, and we use an LD, a load duration factor KD of 1.15. RP width gives you the demand and tension, and this is the tension resistance here, 2085. Again, gets pretty close, but it didn't happen just by accident. We screwed around with it quite a while. So width doesn't match the beam because you don't want a partial width, you want a full width of the beam. So in summary, as we go here in compression, you can see the butt-to-butt connection, taking a lot of load. And I will just mention something right here. I got by myself and I didn't, to see if I can get this to work. Okay. In compression, remember that this compression curve kind of looks like this. In reinforcement, it can look more and more like this. But for the working range of the applied live loads, we can assume that it's direct. I'm not talking the design methodology now. I'm talking about calculating the butt-to-butt compression parallel to grain capacity. And because of this, if you assume that the compression is blocked out, you're going to be assuming wrong. You have to take the centroid of this at, guess what, that's 2/3 point. So always be careful when you're doing a butt-to-butt and FEM. You don't take an average and take the average here. Take the 2/3 point as the centroid, take it triangular. And there's a reason for that, because you've got to be the right moment arm from the neutral axis and the right centroid of activity. This is the total torque, so on. And so this shows you just another little piece of the action here. One of the great things about being able to work with epoxies is if you do run into a spot where you've got a thick glue line. Look at this. I put it in here on purpose because here's a lamination. They had an offset in the finger joint. The offset created a thick glue line well over 4 thousandths, and right there you have a DLAM. You don't see them much, but you do see them from time to time. And so how can you fix this? Well, you can use epoxy and put the squeeze on it and fix it right there. And so that's what we did. We just took care of it and fixed it. And you can see here the completed joint. And that's that. Any questions at this point? Where are we in terms of the scope of our time here? I get set to having so much fun, I lose track. It's 15 minutes to go. I'd kind of like to take some question and answers a little bit more here, because I have a feeling like there's more questions than I'm hearing before I move into the next round of this, away from wood welding into more connectors. Any other questions? I must not be doing a very good job of explaining this, or I'd have you guys would be getting more questions. Okay, Ken?
We got a question there.
Mm-hmm.
Go ahead, Kenny.
Mute's on.
Hi,
Okay,
Dan.
good. Yeah, okay,
Yeah.
good.
The that last slide with the finger joint, and that wasn't a check. That was just a manufactured. That was a
Yeah, that's
defect
right.
glue lam.
That's
What
right,
is the
Ken.
tolerance? Is there special tolerance for this type of glue lam, or is the standard tolerance for glue lamination in timbers adequate?
A typical lamination tolerance for glue lam is 2/1000ths of an inch from one side to the other in difference in thickness. So you're only allowed 2/1000ths of an inch. And the reason for that is because you have the same, if you have the thick on two adjacent lambs on the same side, it creates 4/1000ths, and that's the maximum thickness in a glue line. But this issue wasn't related to the thickness of the lamination, Ken. It was related to an offset right in here at this finger joint. This is a finger joint right here. It's a vertical. You can't see the sides of the finger joint, so it's vertical. And he had an offset. So when they joined the finger joint together, one piece sat above the other. And that offset created a gap. And it took about 7 or 8 inches or 9 inches to cause the gap to close because of the pressure on the clamp when they made the glue lam beam 125 PSI. And so this usually takes about 6 inches to close, and it opens. Well, if you happen to cut the end of your beam right here, because there was a wild end in this beam, what'll happen with the moisture flow in and out of the beam, it'll open up that joint. And so we just were fixing that joint, Ken.
Got it. And so you clamped the beam, or sorry, you epoxy, you filled it with epoxy, clamped it, and that basically closes the joint.
Yeah, fix it up. You know, if we see it, why not fix it, right?
Yeah.
I don't want to have in my FEM, Ken, I don't want to have other things going on that I didn't count on, if that makes sense to you. It's a little DLAM there, but I don't want the migration of stresses around this guy right here in vertical shear, transverse shear at this point. I don't want this glue line separating. Does that make sense what I'm saying?
Yeah.
Yeah. Yeah, good question. What else? I show this on purpose because shit happens, pardon my French. I mean, at the end of the day, what goes on? I mean, real life is about non-conformances. If you got a guy building a bridge for you and he says he's made no mistakes, nothing went wrong, and he had a perfect bridge, he's lying. I'd rather have transparency. I'm going to show you this next bridge in Japan. We had 42 or 46, what we call NCRs, non-conformance reports. We produce a quality assurance document where we document all those and leave a paper trail. 10 years from now, 20 years from now, I'm long gone. That paper trail will be pretty important for people that have to maintain and look after the bridge. One of the biggest problems we have today with old timber bridges is a thin file. We don't know how far the piles were driven. We don't know what the design basis, blah, blah, blah. I want to leave a design brief for working, an as-built design brief, because things change on the site. I want a maintenance manual that tells the owner what to do to look after the bridge. I want to have a quality assurance doc that cites all the NCRs and how they were rectified. You know, I want to have these details available, including working drawings and as-built drawings, to leave behind for the owner to properly manage the bridge. That's the way it should happen. We started doing this with timber, and we're going to raise the game. We're going to raise the bar, and we're going to make timber. I'm in this, teaching this course. I'm telling you, because I'm passionate about timber. I want to see timber succeed in Canada. I want to be able to drive underneath an overpass bridge going across the Trans-Canada someday before I die and see a timber bridge. Why is it that all the way from St. John's, Newfoundland to Victoria, BC, we don't drive underneath one timber bridge? It's not to do with whether it can span. It's not to do whether we can make it durable. It's not to do whether we can carry load. It's not to do with any of these things. It has to do with perception that timber bridges can't do it, and perception is reality. And if the managers, owners, and operators of bridges have never been trained in timber, don't know about timber, have nothing to do with timber, they're going to stay with concrete and steel even when it blows up on them. And I'm like, let's do it with wood. Other questions?
Yeah, I had one other question about the beam width selected. Is it better to pick glue lam laminated beams of one lamination width, or does that have an impact on the design? Because or do you pick wider, shallower
I understand you. If you're going for economics, it's narrow and deep. We usually limit it to 11 because you could see that video of picking up the beam and putting it on edge. You make them narrow and deep, there's a lot of chance for cracking them when you handle them. And so I live with 11 to 1 with the depth. 10 is kind of a little better. I've seen guys use 12. I kind of don't want to stay in the 10 to 11. Sometimes people want height. They got a height issue. There's a soffit height issue, and they want to have the elevation of the pavement, and so they squeeze down the depth of the beam. When you start to go wide and shallow, the economics tend to drop off. It's where reinforcement really shines. When you have a need to have the shallower beams, reinforcement really helps. So it's just one of those things. Can the economics come from narrow and deep? And as long as you don't have a soffit height issue and you don't have a lot of fill issue, then you can use whatever you can get up to. These beams are pretty neat, narrow and deep.
And are you using special lamination on the compression side for improved capacity in these?
I understand you. What I particularly design is I buy blanks. I go on the open market and we go to different laminators and we get basically blanks. And in America, it's V4 2400. That's a 2400 PSI allowable stress bending beam that's got lower grade wood in the middle, higher strength grade on the bottom, and not so high up in the compression. You can buy a balanced beam, a V8 it's called, where it's got high strength stuff on the top and the bottom, and pour in the core. In the deck, we turn them on their sides and we use an all L2 because you can't buy that beam in Canada, but you can in America. And an all L2 has enough fine grain so that it doesn't open and crack a lot in the sun, but yet you can get the treatment you like to get from an L3, which is less dense and absorbs the treatment better. So these beams are different layups is what we call, and placing of better grade wood laminations in strategic positions. Any other questions? Well, I got another one up here. Saw a photo now. FRP was applied to one side of the girder. The side was facing up in the photo. How is it applied to the opposite side? Very hard, Mark. When we're doing it, the guys actually have to get underneath the beam. They're up on blocks a couple of feet in the air or 3 feet, and they get on their back and get underneath and plane it and prepare it and put the RP on it. That's how it's done. Not an easy job, Mark, but that's what they do. You can't have it on, you can't have it standing up because you lose camber. You can't have it on both sides at one time, obviously. So you're going to have it upside and the top side and the bottom side, and it's just part of life. The boys get used to doing it. Other questions? Okay. I'm just going to go through the first part of this. I got 7 minutes and I'm going to take advantage of it because my next few slides are kind of an overview of connectors, and I'm going to feature the Nepean Bridge because you guys, it's the Maritimes here, and you guys have heard about this Rainbow Bridge. We replaced with a arch, an old steel bridge. And I thought I'd just tell this story, and it leads into a lot of discussion about different kinds of connectors. Where I made the statement for part 3 coming up next week was out of sight doesn't mean out of mind. So with that, let's just roll into it. This is the replacement of a steel arch bridge with a timber arch. It's the Nepean Marsh Bridge, or AKA Roger Bacon Bridge. You can see the old steel one here. It had reached the end of its life. It was 48 years old. And the nifty story about this is that this old steel bridge 48 years ago was put in a gap here. There were old timber piles that were cut off at the water line. And this used to be a timber bridge before this steel bridge was put in to have the long span 48 years ago. It's in the highest embedded and exposed corrosion zone in the country, and it did not do well. They didn't keep it primed and painted. It cost a lot of money to do that. And it basically corroded out a tension cord. The piles that were in this bridge for the jump spans that were there when this bridge was built were already 83 years old. Those 83-year-old piles plus 48, now they were talking about 100 and let's say 48 and 83, I can do the math on that, 91, 131 years. And the piles that were 131 years were some 150 to 100 years old. So piles in this bridge that are still there today that we reused were growing in Nova Scotia in 1750. 1750. Does anybody on this call know of concrete structures that have been in place since 1750? What's this story that I hear that timber won't last as long as concrete and steel? We drove these timber piles, they got down below oxygen, and they've been there all this time, and they've just been recertified to go another 100 years. I won't be around to see them out. But let's say they're 130 or 40 years now. We just recertified them for another 100. They'll be 240 years at the end of this life cycle. And they were 150 years when they went in. That means the timber in these piles 100 years from now, when it's reached the end of its design life, will have been 400 years old. 400 years old. So when I hear the story that timber doesn't last, I just shake my head. This was abutment 1. You see the timber piles here with this double cap. You see abutment 2, this, you know, the typical Nova Scotia jump span with the, you know, the Doug fir girders placed close together, 8x16s, and a transverse deck on them, blank. You can see this is the piles being numbered. We're SWT in them. We're doing through compression wave assessment to find how deep the carrots go. And what were the carrots? Well, they vertically drift pinned them. When they vertically drift pin the cap to the top of the pile, the water gets in here. They use meltoid barrier. Another mistake. The idea is meltoid's used between concrete and wood when wood's on top, but not between 2 layers of wood you're going to drive a drift pin through, because then the water follows the drift pin into the bright wood of the pile. The meltoid barrier keeps the water and keeps it from evaporating and neutralizing and equibulating, and it leads to decay in the top of the pile, and you often get carrots. And that carrot takes out the pile and likely the cap. Just poor detailing. And here's on the end of the truss where they installed the steel truss, and you can see the multiple layers of platform created on top of the piles. They put in 5 rows of 5 under each corner, and then a couple of rows of 3 here for transition of the cap. This is one of the old bents that was cut off, and there are other bents you can see if you look in the picture. I'll highlight it, see if I can. Right there, and right there, and right there. There are piles just under the water, and that's when the piles were in the river, and that's when the old timber bridge was there before. They cut them out and put in this long span. And you can see the piles here. So we went in with stress wave timing and PET, pulse echo technology, and determined the depth of embedment, and we determined where the bad actors were and where we were going to need to post them, because I wanted to save these piles and use them. And you can see them here. Saving them to use them. Saving them to use them. Saving them to use them. And we took cores out of them and took the cores through the whole width of the pile. So we had to sample outer, inner, inner, outer. And we've done this thousands of times. It's a basis for a publication that's currently out there now that forms the basis for chapter 9 and S6 for talking about moisture content in timber. It's how we know about moisture content, because we've done so much of this work. ASTM standard test, our group WRD is a code certified test, IAS TL 193, we're a code certified test agency. And so we went and test these components and look at the moisture content here. Look at the specific gravity here. Obviously not some Doug fir piles, and obviously some high times with some Doug fir piles that have been reduced in specific gravity. And we basically zeroed in on the depth by PET using 12,000 feet per second for the wave speed. We're going to adjust that because we've just PET'd Dillmans, where we have a known depth of embedment. We're going to adjust this speed now so we have better knowledge on speeds, because these PET devices are good for steel and concrete. There's not a lot of work behind them in wood. So we were able to get the depth of penetration. You can see here, they also performed a dynamic load test on them, hitting them with an anvil and having their strain gauges and their accelerometers, and come up with these types of capacities. I'm not real happy about having a capacity. Let me see here, move this again in the way. Remember, with substructures, we usually use unfactored loads. This is a factored number of 400. It's a little over what a factored load would be on a typical pile of mine that I would rate. But you can see the axial capacity factor from TDA from these piles in the soil they're in. They're probably driven in this clay soil they're in, that probably didn't get refusal. They run out of pile. And this is the PET embedment numbers in meters. That allowed us to design the sub, to put a new timber arch in here with its corner bearing. And it weighed a fifth the weight of the steel. So I only needed a few of the piles that were in this set of 5. I used them all just for redundancy, but only needed a few percentage of them because it was much lighter. And I had 3 lanes versus 2 to design. The old one was a 2-lane, this was a 3-lane. And so I needed a few piles and I used them all. And we put it into Lucis and did the analysis, as most engineers were. We'd have a transverse cross triple T pattern with transverse laminated deck and a transverse glulam leg. You can see this is the design here. So we started building it off of our design, setting in the new jump spans after we'd trimmed the piles to the proper height to bright to get rid of the carrots and put in the pieces. We used old piles to come up with the pieces, good old pile pieces, because I want to use what we had. And we had the proper detailing for rotation. We had an off-center pin, and we have rotation resistance. We have vertical resistance up and down for uplift and vertical. And you can see them here. These are the typical ways they screw over a timber pile, right? Take rebar and drive it down through your cap into your pile and wonder why the pile goes away after a very short period of time. And it's that understanding of timber that leads engineers to say timber piles don't last. The timber doesn't last. If you're going to drive verticals into the middle, into bright, let water migrate to the middle of the bright and decay them out and create a carrot, and have to change a pile out or change a cap out, well, that's not timber's fault. That has nothing to do with timber. That has everything to do with durability design. So you can see them in here. We're looking at the pile. So we create bright everywhere. You see they're all bright here, all trimmed, because down below oxygen, these piles are as good as the day they were driven. They're set. They're great. So then we start laying the multiple layers of cap to form up their corners for our new truss or new arch going in. And you can see this is the first layer of cap. And then there's a second layer of cap. And here's a third layer that's going to receive that great big arch. And here's shear plywood you can see here to enhance shear, so I don't have to make the whole beam big for a localized shear problem. And you see the thrust rods here, the same thing we pulled the pieces of FEM together with, we have here. What's this purpose? So that when I come time to drop my arch in and I want it to be within a 32nd of an inch, so when I got an 83,000 pound arch lifted with a 500 ton crane, we're not stuck not being able to have it drop in and go over the ends of the girders. So these guys here can be adjusted to move the whole system forward and back to accommodate fine calibration of the gap. This is a lift bucket because I had the jump spans cantilever into the center of the arch to take load off the arch. It's a trick, and reverse the moment. And these guys can be what? Used to level the beam to create level and adjustment. So these are the jumps installed on the bridge. And these are the decks going on with the routes here for a TL4 truck crash proof rail system. And you can see in here, there's the more thrust rods at this location. So we have adjustment over here as well for the whole jump span. It's not good enough to have an adjustment here with the cap at the PB2. You got to have it over here too. Why? Because I need a rotation bolt here. And if I got a different span length, because things are a little different, and I've manufactured it beforehand, post-treated after machining and assembly, and it gets on site and everything doesn't fit, I'm tempted to drill a bright. So with this thrust rod, I can use this vertical coming off the cap, use the thrust rod to adjust and end up with no bright. It's durability, guys, durability. Z clips here up top that go in underneath the deck. The vertical lag doesn't pass through the top and allows adjustment because the transverse deck can shrink and expand, and longitudinally it doesn't. There's the TL4 in place. And you can see here putting the back wall in. This is the temporary support for the 500 tonner. And this is assembling the arches, pre-assembling them in components in a plant that we rented close to the bridge site. And this is using a ram and 60,000 pounds to push the pin through the finders. It's a big push. They're all precision made, but guess what? Steel shrinking, expanding a little bit, and the temperature changes. It's a lot of push. And then we graphite treat them because the push takes the galvanizing off. So we graphite them. You see here the assembled, pre-assembled pieces. This is the transverse center span triple T's. We have the fillet blocks, and we're going to glue onto this guy here along a transverse vertically laminated beam, forming a triple T. And this is where we're basically assembling the truss alongside of the jump span. We use the jump span to assemble the truss because we're going to drive a 500-ton crane right out on the jump. You can see us putting the pieces together with the pins. And we use these, of course, you know, tilt up lateral supports, shoot into the asphalt, because these are big, and falling over on somebody in a windstorm wouldn't be a great idea. You see us finalizing the assembly here and the hanger rods. This is just prior to the hanger rods. These guys were all assembled, as you know, prior to that in the facility. These are hanger rods with pipes. What's the pipes about? Well, we put them in a cradle so that they rotate. They're free to rotate and find vertical alignment under different loads. We have adjustments here for them so that we can adjust this arch to take out slip distortion. We didn't glue the shear plates in because I could get rid of slip distortion by adjusting. And we did adjust these after they were even built and assembled. We adjust with a long cheater bar and a zoom boom and get up there and adjusted the torque on these nuts and raised up the bottom with the whole deck on it. You see us, that's lifted in with a 500-tonner on the jump, and we're getting ready to lift him in. There he is, going into place on the jump, setting into place. With these adjustments, you can drop this guy into place with a fine detail and be a 30-second out and get it in without tearing things apart or brighting. We don't want to bright. And there's where we finish with it in play. And it's 3:07. And I ran you 7 minutes over, and I apologize, but this gets us just nicely to a spot for next session. Any question before we leave? What are carrots? Well, we call it decay carrots, Bob, if we have a pile top. If I have a pile, oh, come on now. Come on, don't do this to me. No. I'm going to do it. Sorry. So there's piles right here. No, come on. Why is that? There's piles here. When I get a pile and I put a cap on top of it, and I put a vertical drift pin right down through it, and I put a meltoid barrier. This is so typical. It's a terrible detail. One of the worst details in timber engineering in North America today. I hate it. It's a terrible design detail. So what happens is water follows this guy down, gets in here around this guy in the bright wood. Meltoid keeps him from breathing. And in this area here, it decays and forms a decay carrot. It looks like this. The annulus thinner up here, thicker and thicker, and this decay carrot travels down the piece, and we use SWT device to find bright so we know where to amputate that carrot off. It's called a decay carrot. Any other questions? Okay, Ken, what do you got?
Yeah, go ahead, Kenny.
Yeah, the TL4 crash barrier, how much of that is that replaceable, or is that also intended to be 100-year service life? Like what?
I understand you. So in case of snowplow, yeah, if snowplow hits it, Ken.
Yeah.
Look, the TL4 rail system is a specific rail system. In other words, it's a tested empirical rail. You can't change it. It has a certain detailing set, Ken. And there's a TL2 and a TL4 that were tested by USDA Madison, and we use those specific details. You have to have a certain deck thickness, blah, blah, blah. If you hit it with a snowplow or pieces of it get decayed or beat up, you can replace the pieces kind for kind, and it's not glued in place. It's all mechanical. So it's pretty easy to do that. Does that make sense?
Yep.
Other questions? So on a small scale, Brian Hook, a small scale, is it good to put a strip of tar paper over a floor joist on a residential deck. If you're going to drive a nail through the deck into the top of the joist, the answer is absolutely not. Don't put your joist, your deck planks onto the joist with vertical fasteners that go into the joist. It's the kiss of death. It's why decks only last 10 years. It's one of the worst things we do. There's the bear clip, the dowel clip. There's several ways to join deck planks to joist without going vertical from the top down. It's the worst thing we do to shorten the life of a piece of deck. Second thing, we buy treated deck and then trim all the ends and expose bright. We cut the pieces into pieces, expose bright. And then we have water-based treatments with very low uptake and very poor depth of penetration. Buy in size stuff as you can. Really, as I used to say about a bomb, you put lipstick on a pig, it's still a pig. The bottom line of the story is most of these treated, what we call residential deck systems, are non-commercial. You don't see them used in the highway side. They just don't have the uptake, the depth of penetration, and you're brightening them all over the place with verticals that come from the top and cross-cutting the ends. Anything else? Another question?
Okay. I think we'll wrap things up there, Dan.
Yes. Yeah, good.
Thanks for that presentation. And thanks everyone for sticking around, and we'll see you next week for part 3.
Yes, thanks everyone for putting up with me.